Hello, my name is Gavin Baker. I'm from Melbourne, Australia, and I'm going to be talking about sound visualization today. Here's a great example of visualizing sound. It's the visualizer that's built into iTunes, and you can see very clearly how the visualization is responding to the beat and the different frequencies in the music. It's a very effective way of seeing what you're hearing and associating it with that content. Here we can see the first view, which is the oscilloscope. It's a waveform view, which you'll be familiar from if you've used a digital audio workstation. On the vertical axis is the amplitude, which could be measured in volts or in dBFS. And on the horizontal axis, we have time. And so it shows amplitude versus time. And we can measure the frequency of a signal by measuring the period of one cycle here and taking the reciprocal to get the frequency. That's not a very useful thing to be able to do, which is why a spectrum analyzer is a very useful thing. But this is the sound of a trumpet playing middle C. And you can tell that it's a very nice even tone, and there's actually some slight variations in the amplitude as we go along, and then it trails off right at the end here. Let's hear that again. Now if we zoom out, we can see that the waveforms get closer and closer together until it's a little bit hard to actually make much sense of them, and then eventually we can see individual notes over time. Now here's an example of using the oscilloscope view to visualize a tone that's a sine wave that's been generated at 440 Hertz, which is concert pitch A, and this is the original tone. Not the most beautiful of tones, but that's what it is. Now this is an 880 Hertz tone, so that's twice the frequency of this one, and you can see that there's twice as many cycles in the same time. And so we can see that the frequency and the amplitude can change independently of one another. Next we're going to have a look at the spectrum analyzer. This shows the distribution of energy at different frequencies in a signal. So we're looking at the 1 kilohertz signal that we've generated up here with an amplitude of 2 from -1 to +1, and here we see the spectrum analysis is showing a 1 kilohertz peak with an amplitude of 2. That's exactly what we've got here. Now here we've got a bit more of an interesting sound to listen to. We're listening to the sound of an acoustic guitar being plucked, and it's plucked several times at slightly different volumes. So let's listen first. So you can see in the oscilloscope that the amplitude peaks when the string is plucked, and then slowly decays and peaks and decays and peaks and decays, and the frequency is about the same because it's the same string and the same note that's being plucked. But here in the spectrum analyzer we can see that there's a fundamental frequency down here which is has lots of harmonics as well, and that's what gives it the timbre, the characteristic tone of the guitar. So there's the fundamental frequency down here, and then these primary harmonics, and then lots of little ones which give it that rounded out sound. Now what's useful about this is that it lets us associate the numbers with what we're hearing, and it shows us the different energy at the different frequencies. And the problem is though that it's a momentary picture, so it doesn't show how things change over time, and for that we need a slightly different visualizer. Now the last visualization technique that we're going to look at is the spectrogram. This is definitely my favorite, and it basically combines the first two that we saw, the oscilloscope and the spectrum analyzer, into one visualization for the full picture of the sound, and it really relates best to how we really hear sounds. So on the vertical axis we have the frequency, and on the horizontal axis we have time, but there's another axis which is the z-axis, if you like, or in this case it's actually rendered as colors, and that's the amplitude or the energy in that. So it's you can see how it directly correlates with the oscilloscope above. So each time the guitar is plucked, we'll hear we can see that we have the fundamental here with the most energy, and we've got a couple of harmonics up here. There's 1, 2, 3, 4, 5 in the first one. They're getting fainter and fainter, but they're still there. So we can see that the root, or the fundamental note frequency here, has these clear multiples of the harmonics, and there's this little extra bit at the start of each note, and that's the plucking sound where the finger strikes or picks the string. So thanks for listening to my little presentation on sound visualization today, and I'm going to leave you with an example of all of these three visualizations together, just with a very simple little range of different guitar notes to show you everything together and how they relate. So yeah, thanks for listening.